Hello everyone, this is Professor DePaulo. Welcome you back to Psych 220, fully online behavioral statistics. And this week's topic is going to be measures of central tendency, which corresponds to chapter 3 in the textbook. So the learning objectives for chapter 3 include understanding the purpose and the measuring of central tendency. So why is it important? Why are we doing this? Number 2, define and compute the 3 measures of central tendency. That's the mean, median, and mode, which you should be familiar with in some manner from previous courses in your elementary school, middle school, and high school. Learning objective 3, describe how the mean is affected when a set of scores is modified. So what happens if we add a constant or multiply or divide by a constant? What happens to the mean when we apply a linear transformation to all scores of the data set? Number 4, describe the circumstances in which each of the 3 measures of central tendency is appropriate to use. Number 5, explain how the 3 measures of central tendency are related to each other in both symmetrical and skewed distributions. And number 6 is draw and interpret graphs relating to these measures of central tendency, more specifically the means and the medians. So just a brief overview of this chapter on central tendency. We know that central tendency is a statistical measure. It's either the mean, the median, or the mode. And we look at it as a single score that defines the measure of center, the center of the distribution. So if you were to look at a distribution of scores, what value would describe the middle or the center? And you want to find this value that best represents the entire group. Most of you might say, well, the mean is used for everything, and that's true, the mean is kind of used for everything, but the mean is not always the best measure of center. Sometimes the mean gets distorted, it gets pulled in various directions, and it becomes kind of an arbitrary measure, and you could see that in distributions like salary, annual salary in the United States. So if you look at the reported annual salaries in the US, you see that the annual salaries in the US is pretty high. And you're thinking, like, how is this possible? Like, so many people are doing pretty well in this country, and yet, you see the big, gap, wealth divide, et cetera, and it just kind of boggles your mind. Well, that's because they're reporting the mean, and the mean is going to be offset by like some major, outliers, right? Like billionaires or multi-billionaires, and they kind of pull everybody in their direction, and that doesn't really give you a good measure of what the typical economic condition is or financial condition is for people living in this country, because the billionaires are distorting it, the 1%, right? The rich get richer and the poor get poorer, and that can be considered an offset or a consequence of capitalism. I'm not going to go into whether capitalism is a good system or not, but anyone can kind of show with statistics the point they're trying to make. So if the country is doing well financially, look at the mean income in the country. It's, people are making a lot of money. And in reality, that mean is distorting the actual picture of what's going on right now. So here is just a graphical representation of the measure of center, right? So where do you want to really draw the middle point, or what's the best representation of the middle of the distribution in each of these 3 examples? So if you look at example A here, you have a symmetrical distribution. That means that the left and the right half of the distribution are mirror images of each other. It looks like there's one peak of that distribution around 5. And since it's symmetrical and there's one peak, we can say that 5 is the middle, right? So the best description of what the middle is here is 5, because the left and the right-hand side are the same, and most of the scores are kind of in the middle. And this is what we call a normal distribution. And that's the beauty of the normal distribution, is that most of the scores are in the middle, and very few scores are in the extremes. And we have a good idea of what's going on when scores follow a normal distribution. And in psychology, a lot of scores do follow a normal distribution. The vast majority of them do, with the exception of things like reaction time. And time is kind of a tricky variable. But as in the previous example, when you're looking at distribution of wealth in the country, that definitely does not follow a normal distribution. And so outside of the psychological domain, you're going to see a lot of distorted distributions or non-normal, maybe non-symmetrical, maybe some bimodal. We're going to talk about that too. If you look at figure B here, that's definitely not symmetrical. The left and the right halves of that distribution are not the same. Whereas in example A, you saw that 5 in example A was the most frequent score. In example B, 8 is the most frequent score. The difference is that the 8 here in example B is all the way to the right. It's all the way to the extreme. It's not what we consider the middle. Whereas in example A, it was the middle, the most frequent score. Here it's not. So where's the middle of this distribution? Well, it's to the left of 8. Right? 8's the high point, but the middle, the true middle, is to the left of 8. And so this example B here would be considered negatively skewed because the tail of the distribution is to the left. So this is a negatively skewed distribution. And the mean of negatively skewed distributions are always pulled in the direction of the tail. So the mean here is going to be pulled towards the low end. Because those outliers, the people that are scoring here, 1 and 2 and 3, those are outliers. They don't belong with the rest of the data set. They're pulling the mean. They're saying, come here, come here, come here, come towards me to balance it out. And there's different ways we can think of this. We can think of this as a balance beam, a seesaw, a fulcrum, and I'll explain that afterwards. And in example C, this is definitely symmetrical, but it's not normal because with normal you have one peak. Here you don't have one peak, you have 2 peaks. So you have 2 symmetrical peaks. And where's the middle going to be? If it's symmetrical, the middle looks like it's going to be around 5 here. But if I gave you 5 as the measure of center, that doesn't really tell you much about what's going on in this example. Here you have 2 separate groups, and what we call this is bimodal. So you have a mode at 2 and you have a mode at 8. It's a bimodal distribution. You have 2 symmetrical but separate groups, one corresponding to a high achieving, people that scored high on whatever variable is being measured here, and then one group corresponding to people that scored low. And we do see this in academics where you have different groups of people. You do see this in terms of other variables that can lead to changes, right? So if I wanted to look at salary between men and women, now salary between men and women has really decreased. It's become very close over the last couple of decades. It's becoming closer. I'm not saying that it's the same, it's not. So men do make more money performing an equal task compared to women. We know this. We disagree with this. This is ridiculous. It doesn't reflect our society or our concept of what our society should be, but that's what's happening, right? So it used to be 70 cents on the dollar. That has gone up, but there's still a disparity there. So if I was looking at salary and I saw a distribution like this, I could say one group, the group that's making a little bit more, would be men performing a job, and the group that's making a little bit less is women. Now, it would be closer together than this, but you would definitely see 2 groups like this if you did separate men and women. You may also compare these 2 groups to younger and older people in the workforce. So younger people in the workforce performing a certain job, they may make less money just because they don't have as much experience compared to older people. Now, older people might have more experience, might be performing a different job, but really, what's a different job? It's a promotion. You're doing a lot of the things you've done before. You're just building off of it. So if I looked at this distribution and see, I could say it's younger folks are in the lower part of the distribution, making less money. Older people are making more money, right? So when you have 2 distinct groups in your data set, you have to then analyze what's going on here. Like, why do I have 2 groups? Why do I have 2 different sets of people. It's almost as if you have two different populations, which you may, in your distribution. And that's really important in terms of analyzing your data and figuring out what's going on here. So the previous figure showed that there's no single best way to measure central tendency, although the mean is the most widely used measure and is the preferred measure if possible because inferential statistics, which we're going to be doing later in the course, right now we're doing descriptive statistics. We're just looking at the shape of the distribution and what's going on with the data, right? Try to make sort of have a basic grasp of what our data are telling us. But eventually we're going to be using our sample to draw conclusions about our population of interest. And the best way to do that is with the mean. So the mean is preferred, more than the book is even stating that it's preferred. So if you're doing any kind of higher level analysis, you're mainly working with the mean. Now, granted, that's if you have interval or ratio scale data, your variable is continuous, right? It's interval or ratio scaled. And thankfully, most of the measures in psychology, even questionnaires, are considered interval scaled, so we're good with that. And then we want to also have a normal distribution, of course. In psychology, we tend to have the vast majority of variables being normally distributed. So this all works for us as researchers or psychologists, people studying, right? People doing scientific work, is that we have some nicer distributions to work with, and therefore we can use the mean. Now, if your distribution is really skewed or bizarre in some way, you have bimodality, or you have multiple peaks, what we call multimodal, then you can't do it. Then you're kind of out of luck with doing more advanced work on it. So you want your distribution to be one curve, one peak, symmetrical, what's called the normal distribution. So the mean. The mean is, in my opinion, by far the most useful measure of center. Now, that doesn't mean it's the best measure of center. So I said useful. Useful means that the mean allows us to do a lot of analysis that the median and the mode don't allow us. The median is a better measure of center if your distribution is skewed, but you can't do any inferential stats with the median. So if you can use the mean, if your data is close enough to being normal that you can use the mean, you're going to use the mean. And the mean in the population is denoted as mu, the Greek letter mu. It looks like a U with a little curve here on the left-hand side. That's the Greek letter mu, mu. And that is the population mean. That's a parameter. So that's the mean of the population. Remember that parameters refer to populations and statistics refer to samples. So if I'm computing the mean of the population, I take all the values in the population, which is sum of x. X is each single score, so if I sum x, that means I add up all the scores in the population. That bracket thing you see here is called sigma. That means add everything. So sum of x divided by n. Capital N is the total sample size. So it's the sample size of the population. So add up all the scores in the population, divide by the number of scores in the population, and you have the population mean. Obviously, you're not going to find this because the population is too big. And unless you're dealing with an incredibly rare disease where you have access to everybody, like there's 30 people in the world that have this, and you travel around the world and find those 30 people, and you study all of them, then you would study the population. That would be the only scenario, and that's not even realistic. No one does that. That's the only scenario where you're studying the entire population. I mean, even if I were to limit the population to BMCC students, there's 25,000 of them. There's no way as a researcher I can study that, right? And we talked about the census last time. Yeah, the census is supposed to be a measure of the population, but it's really not, because not everyone's completing the census, and the census is generally not giving a good representation of the population. It's giving a representation of people that actually complete the census. What about the homeless people, right? What about people in jail? Now, I guess you can go to the jails and measure the, and put that into the census, but are you going to go on the street and approach all the homeless people and get their data for the census? Are you going to be able to find them all? That's the problem. So you're not really getting access to the population, even with something like the census. So in psychology, it's impossible to measure the population, so we measure the sample. Sample should be a representative subset of the population. To find the mean of the sample, we call the sample mean M, capital M. You may see it referred to in other books as X bar. X bar, X with the little line on top of it, horizontal line on top of the X, is generally how it's written in 90% of the textbooks. The reason this textbook is using capital M is because that's how it's written in a journal article in psychology. So in psychology, they use capital M to represent the mean in the journal article. So the book is saying, well, since the journal article has used capital M, we're going to use it in our, notation. So they're the same thing. X bar or capital M means mean of the sample. The population mean is always mu. And you add up all the scores in your sample, sum of X, divide by lowercase n, which is the sample size of the sample, and that gives you the arithmetic mean, right? There's different types of mean. You have geometric mean. We're not going to talk about that. We're just talking about the arithmetic mean. You have harmonic mean. You have other things. We're not going in those directions. This is basic arithmetic mean. So alternative definitions for the mean, it's the sum of scores divided by the number of scores. That's what it is. You can think of it as the amount each individual receives when the total is divided equally among all the individuals. So it's basically what everybody gets when you share equally. So if you divided the wealth up equally amongst the number of people in your sample or population, that would be what everybody gets. That's the mean. Everybody gets the mean. You can think of it as the balancing point of the distribution. So if you were to look at it as like a seesaw, it's where you would put the fulcrum, right? Where you put the actual lever to balance it out. And that's what we have here in this slide. The mean as a balancing point. And you see there's 1, 2, 3, 4, 5 scores here, 5 people, and they each have scores from 1 to 10. And 2 people scored 6, 1 person scored 10, 1 person scored 2, 1 person scored 1. If you were to balance this out so that, the seesaw doesn't, or the, what do they call this? This is a simple machine in physics, right? The fulcrum, right? On the bottom here. If you were to balance this out, the scale, you would put the mean around 5. So 5 would be the balancing point. And the reason 5 is the balancing point is the mean is calculated as distance, right? So if you add up the distances, if you look at the person that scored 1, they're 4 spaces off from 5, right? The person that scored 2 is 3 spaces off from 5, 3 less than 5, right? The person that scored 6 is 1 greater than 5. There's 2 of those people, so that's plus 2. And the person that scored 10 is 5 greater than 5, so that's 5. So you have plus 2, right? Plus 1 for the people that scored 6, that's plus 2. And you have a plus 5, so that's plus 7. And then the person that scores 2 scored a minus 3, and the person that scored a 1 scored a minus 4. When you add up all those numbers, you get 0, right? So that's what we call the deviation scores. And you're going to be learning about that when we calculate variance and standard deviation. So the mean of 5 here balances it out. It equals the distances for all of them add up to 0 from the mean. Now, if you have outliers, the outliers are going to shift that fulcrum, right, that mu, the mean, in the direction of the outliers. So let's say I added a score that was 100 to this setup here. I added a score of 100. Well, what that's going to do is going to pull that fulcrum all the way to the right towards the 100. It's like the seesaw. I guess they still have seesaws in the playground, right? They used to. I don't know if they still do. I mean, they're getting rid of all these playgrounds now. But when you used to be on the seesaw, you used to sit on one end and somebody else would sit on the other end when you were a child, or maybe you do it as an adult. I don't know, whatever works for you. And you'd go up and down on the seesaw, right? But then if you remember, like if you were like really light and then someone much heavier kid sat on there, right? You'd go flying up in the air. So think of that much heavier person as the outlier. And so the fulcrum, the middle point, has to be moved in their direction in order to keep you balanced, right? Otherwise, what happens is if you're the lightweight and the other person's the heavyweight, you go flying in the air. That's not balanced. You got to move that fulcrum point. Obviously, on a seesaw, you can't move the fulcrum point, but in this theoretical example, you would move it towards the bigger number on the positive end if there's a positive outlier. And on the negative end, you'd move it to the smaller number if it's a negative outlier. So any outlier, which is an extreme score, will always pull the mean in its direction. That's basically the take-home point of this. Now, you can also calculate a weighted mean. A weighted mean basically means you have two samples, and they could have different sample sizes. They could have technically the same sample size. But if I have two different samples and I want to find the mean of those two samples, or three samples, or five samples, or 10 samples, it doesn't matter, right? In order to find the mean of those samples, you would add up each of the sum of x's for those samples. In this case, we have two samples, sample 1 and sample 2. I add up the sum of the values in the first sample of whatever I'm measuring, and I add up the sum of the values in the second sample of whatever variable I'm measuring, and I divide that by the sample size for the first sample and the second sample size, and that gives me the overall mean. This is known as a weighted mean. And this is kind of how you figure out your GPA, right? So if you score an A in a class, right, and it's worth 3 credits, you multiply the A, which is considered a 4. A is 4, B is 3, C is 2, D is 1, F is 0, right? That's how you weigh it. And you multiply that by the number of credits. So if I scored an A in statistics, statistics is 3 credits, so it's 4 times 3 gives me 12. And then you do that with your other courses. So if you had a 4-credit course in biology, you just scored a C, well, C is 2, right? And then you multiply that by 4, the 4 credits, and you get 8. And you keep doing that with all your classes, and then then you divide it by the total number of credits you've taken. So most of you take 12 or 15 credits. Some of you take less if you're part-time or non-matric. You divide it by the total number of credits. So once you do that, you calculate your GPA. And that your GPA is a weighted average because some courses are 3 credits, some courses are 4 credits, some courses are 6 credits, some are 1 credit. And so whatever you get has to be weighed by how much that course counts. It's better to get an A in a 4-credit course than it obviously is in a 3-credit course or a 1-credit course. It's worth more. And so you have to weigh it by the total number of credits. If you have a frequency distribution like we talked about in chapter 2, here's how you would actually compute the mean from a frequency distribution. You would take the frequency of each score, which is under the F column. You'd multiply that frequency by the actual value of the score, and that would give you the Fx column. So 1 times 10 gives you 10. 2 times 9 gives you 18. 4 times 8 gives you 32. 0 times 7 gives you 0. 1 times 6 gives you 6. So that Fx column is just the frequency times the score, and then add up that Fx column, and that gives you basically your sum of x. That is your sum of x, the sum of fx. If you didn't have the frequency table, you would have to write them all out. Each individual number would have to be written out. So you'd write 10, and then the next number would be 9. Then you'd have another number that was 9 because it occurs twice. Then you'd have 4 8s. You'd have 0 7, so you wouldn't write 7. And you'd have 1 6, and you would add that string of numbers. But with the table, it's just easier just to multiply f by each x score, in this case quiz score. It gives you the fx total column. Add up that fx column, that gives you your sum of x. So sum of fx here is your sum of x, 66. Your total number of scores, your n, is the sum of the frequencies. In this case, it's 8. And then take 66 divided by 8, and you get 8.25. And that is your mean. So it's very simple. You just multiply the columns across, and then divide by the total of the f's, the sum of the f's, which is your sample size. So here's a problem to check on. If you have 12 scores that have a mean of 8 out of these 12 scores, what's the value of the sum of x? Well, this is just reverse engineering the problem. So if the mean is equal to the sum of x over n, then all I have to do to find the sum of x is multiply n times the mean. So in this case, my n is 12. And my mean is 8. If I multiply my sample size times the mean, I will get my sum of x. 12 times 8 is 96. And obviously the answer is 96. 96 is your answer. Very easy. To find sum of x, multiply the mean times the sample size. And that gives you sum of x. So some characteristics of the mean. As I mentioned before, if I change the value of a score, I change the mean. If I add or remove a score, I change the mean unless the score added or removed is exactly the same as the mean. All right, so if the mean is 7 and you remove one value that happens to be 7, the mean stays at 7, right? Because you're removing the same value of the mean. If you add a score of 7 to your data set and the mean is already 7, and you add a 7, the mean stays at 7. So if you change the number, if it's something other than the mean, it's going to affect your value. If I add or subtract a constant from each score, that changes the value of the mean by the same constant. So if I add 3 to each score in your data set, then I have to add 3 to the mean. If I divide each score by 2, then I have to divide the mean by 2. You have to do it to every score, though. It must be, consistently applied. And that's same with multiplication division. So whatever you're doing to every score, you're going to do the same thing to the mean, whether it's addition, subtraction, multiplication, or division. So here's another example where the mean is 7. So I have 5 scores here. I have 3. I have 2 6s. I have a 9, and I have 11. When I add them all up, I get 3 plus 12 is 15, plus 9 is 21, plus 11, 3 plus 12, 15 plus 9 is 24, plus 11 is 35. 35 divided by 5 scores gives me 7. That's my mean. Now, if I add a score here, that score is going to affect the mean unless I add a 7. So if I add a 7 here to 35, I get 42. And if I divide by 6, as I added one score, I get 42 divided by 6 gives me 7. So the mean stays the same if I add a 7. Or if I subtract 7, the mean would be the same, right? However, let's say that I'm adding 1. 1 could be considered an extreme score here. So let's say I add one person, they scored a 1 here. So now I have 35 plus the 1 gives me a 36 as my sum of x. And now I have 6 scores instead of 5 because I added the one score, which is a 1. So 36 divided by 6 gives me 6. So you see if I add a low score, an extreme low score like 1, I'm pulling the mean in that direction. So if I add 1 here, which is a low score, the mean then shifts from 7 to 6. The mean is being pulled in the direction of that low score. Now, obviously, the farther away the score that you either add or subtract from the problem from the data set, the more effect it's gonna have on the mean, right? So if I add a 1, I'm only shifting the mean from 7 to 6. However, if I add 5,000 to this problem, well, what's happening to the means? If I add 5,000 here, I go from 35 to 5,035. 5,035 divided by 6 gives me 800 something, right? So the mean would go from 7 to 800 something if I added 5,000 as a score. Now, that's not realistic. I mean, if you're studying something, you're not going to have, unless you have a data entry error, you're generally not going to have that big of an extreme, right? But you see that the point here is that if I add an extreme score or take away an extreme score, it's going to have a big effect on the mean. And the further that score is from the mean, the more leverage it has, the bigger of an effect it's going to have overall. So adding a 1 here only shifts the mean 1 point to the left. But if I add 5,000, it's shifting the mean 800 something points to the right, because that 5,000 is so far away from 7. And that's the problem with outliers. The more extreme they are, the more they tarnish your data set, the more they disrupt the ability to actually use the mean. The mean is not useful when I have extreme scores. The more extreme the score, the less useful the mean is as a measure of central tendency. Here's another problem. You have 7 scores with a mean of 5, right? So the sum of x here would be 35. All the scores are doubled. So if all the scores are doubled, what's going to happen? Well, if all the scores are doubled, the sum of x is going to be 70, and 70 divided by 7 is going to give you 10. So what's happening is if I double every score, I have to also double the mean. So the answer here is going to be 10. Surprise, the answer is 10. Very basic. So simple linear transformation. If I double all the scores, I double the mean. If I triple all the scores, I triple the mean. If I take 1/2 of all the scores, I take the mean and I divide it by, divide it in half, right? It's half of the mean. So whatever you do to all the scores, you do the same thing to the mean, no matter what the situation is. But you have to do that to every score. It has to be consistent. You must multiply by a constant, divide by a constant, add or subtract a constant to every single score in order to have that effect on the mean. Now we move on to the median, which is not as useful as the mean in terms of doing data analysis. There's not much inferential stats you can do with the median. However, if your distribution is not normal, if it's skewed, or if it's, I guess if it's bimodal, it's probably not a good idea either. But if it's skewed, the median will be the best measure of center. And guess what? If your distribution is skewed and you're trying to test a hypothesis with advanced statistics, like, well, not really advanced, but advanced of what we're going so far, like t-test, ANOVA, things like that, you can't do those inferential tests on a skewed distribution because those tests require you to use a mean and they require the distribution to be normal. If you're using a median, it's because your distribution is skewed and you're saying that the median is a better representation of the center of the distribution because the mean is being pulled in the direction of the skew, so it's not a very good measure of the center. It's going to be out in the tail somewhere, either the right tail. If it's positively skewed distribution, the tail's to the right, the mean's going to be pulled in the right tail. If it's a negatively skewed distribution, the tail's to the left, the mean's going to be pulled in the direction of the tail, which is to the left. So the median is going to be more towards the middle, right, away from the mean, away from the tail. That's a good visual description of the middle of the distribution, but statistically, it's not as useful. So the moral of the story is if you're using the median as a measure of center and you're testing a hypothesis, you're doing research, you're in trouble because then you can't do the basic test that we're going to learn in this course. You would need to do something called a non-parametric test, and you really don't want to go there because it's not good for your research. It's possible to do it, but it's going to be a problem. Which means the bottom line is you want your data to be normally distributed. You want it to look like a bell curve or something close to that. If it looks completely skewed, you're going to have a problem doing the analysis, and then you're going to have to think about transformation of the data, and that's a topic for another course. But for this course, the median is the center of the data, and it's best used when your data is skewed. It's also known as the 50th percentile. So if you were to find the percentile rank, it'd be the 50th percentile. And this is stuff that you should know how to do. I mean, this is the really, really basic stuff, like beyond basic stuff. Locating the median, put the scores in order. So here I've put the scores in order for you. If there's an odd number of scores, then the median is the middle score. So if the scores are in order 3, 5, 8, 10, 11, the median, that's 5 scores. The middle number, the middle number is 8 here. So the median is 8. So when you have an odd number of scores, it's the middle number. When the scores are placed in the correct order, you have to arrange the scores from smallest to largest. That's where people screw up. They don't put the scores in order. You must put the scores in order first, and then it's the middle number if you have an odd number of items. If you have an even number of items, put the scores in order first, and then average the middle 2 scores. So in this case, 1, 1, 4, 5, 7, 9, there's 6 numbers. The middle 2 are going to be number 3 and number 4 out of those 6. Those are the middle 2. And if you average the middle 2, I get 4 plus 5 divided by 2. That gives me 4.5. That's the midpoint, right? So the average of those 2 middle scores is also known as the midpoint. And here it is 4.5, so that's the median. And this is probably something you already know and done a million times. And if you take them out 150, you've done it a million times. And it should just all be reviewed. Which means that the first exam should be something that you do really well on. Because so far, most of this stuff is not really, I don't know, it's not really that interesting. It's kind of foundational work. It's not something I really like to think about on a regular basis. I'd rather do something more worth like talking about. But you got to have the foundation. So this stuff has got to be like really clear, really solid, that if I gave you the exam, you would get 100. There's no way you can get this problem wrong. Now I say that because people always get these problems wrong. So in my mind, I'm saying to myself, I don't know how you could get this problem wrong, but it always happens. It's like, it's unbelievable. So this seems simple. This might seem boring to you. This might seem rehashed and you've had this already. Why do I have to do this? Don't say that. Study it, practice it, master it, because students always screw these problems up on the exam. Now, the exam is going to be online, so I don't know how that's going to differ from the regular exam. I mean, I think it's going to be an easier exam. If this class was done in person, I'd be doing a lot more material, but given the fact that, we're doing remote learning and this is not the best way to teach the class or the preferred way to teach the class, in my opinion. I'd much rather do this in class. But given the situation, learn the material, get your grade, learn some things, ask questions, ask me other questions. Ask me questions about a whole bunch of things, even things that I'm not testing you on. If you're interested in something, send me an email, come to Zoom, whatever. I'm happy to talk about it. Um, but get this stuff down so you're like acing it's 100%. This should not be an issue at all. If there's an issue with this, come see me. We'll talk about it. I have my sketch pad, which is torturous to write on, and I write sloppy on the board, but this is like a whole new level of sloppy. I'm definitely not an aspiring graphic artist or painter. I don't know how these people do. I mean, if you do this sort of thing, it's amazing how you can like sketch and paint on these tablets without even looking to see what you're writing. You have to look at the screen and do it. It's just, for me, it's a level of creativity that I don't possess. So we'll stop it there. I think I'll have to stop talking now. Okay, so now we move into something a little bit more, requires a little bit more of an effort, a little more cognitive effort to understand. And this is finding the precise median for a continuous variable. So the stuff we did before is if you have a discrete data set. A discrete variable is a variable that takes on a finite number of values where you don't have intermediate values. So you generally have just whole numbers or integers because you can have well, I get probably not negative numbers in these measures, right? But you have counting numbers. So how many siblings do you have? You have 0, 1, 2, 3, 4. You don't have any in-between values, and you don't have negative values, obviously. Those are discrete variables, right? How many cars do you own? How many jobs do you work? All that stuff. There's only a finite number of values you can have. If you're dealing with continuous variables, which is anything that has intermediate values to it, right, has technically an infinite number of values because you can keep dividing it up into smaller and smaller parts. If you have these continuous variables, the median is not as simple as what we just did. What we just did is mainly for discrete values. With the continuous values, you don't have the actual histogram, you have a curve. And so to find that 50th percentile of the curve, you kind of really have to do a little more work. And I'm going to give you some basic examples, walk you through a basic example of this. But it can be a little bit more tricky with a large number of scores. You wouldn't really be able to do it by hand. You would need to then use a table, uh, the um, the normal distribution table that you're going to learn about in the future, where you actually look up the areas in the curve, because that's all done through calculus. And the calculus is not required for this class, obviously. So to find the precise median of a continuous variable, what we have to do is we have to look at the actual bin, the actual value that separates the left half and the right half of the curve. And we have to determine how much of that value, of that bin, of that value, of that number, how many people that score that particular score do we need to take and put them on the left side versus the right side. And compare that to the number of people in that interval. So that sounds very abstract. It's not. I'm going to show you an example. So here's a very simple example of finding the precise median for a continuous variable. So we have 1, 2, 3, 4, 5, 6, 7, 8 scores here. And they're represented by blocks. As you can see, the most frequent score here, which is technically the mode, is 4. You see that in figure A, right? In order to find the median, I need to find the middle point, the 50th percentile. So the 50th percentile means that 4 of the 8 blocks have to be to the left of the median, and 4 of the 8 blocks have to be to the right of the median. So I need to draw a line that divides 4 and 4, left side and the right side. Divide this completely in half. Well, it's not easy because I have all these people scoring 4. And so I know that I count, there's one person that scored 1, there's one person that scored 2, there's one person that scored 3, so that's 3, but I know I need 4 blocks on the left and 4 blocks on the right. So I need to kind of steal one of those blocks that are that are listed in the group that scored 4 here. There's 4 of those blocks. I need one of those blocks out of 4. So what I have to do is if there's 4 blocks there and I need one block, I need one block out of 4, so I need 1/4 of each block. And hopefully that makes sense. I only need one of those blocks listed under 4 to the left of the median, and I need the other 4 to the right, right? So I only need one of those 4 blocks on the left. So I can't take all 4 of those blocks. I have to take one. And the way I take one is I take 1/4 of each block, right? So I need one block out of 4, which is 1/4. And if you look on the right, what the text has done is it's drawn a line through 1/4 of each block. Now notice that the blocks are centered above each number, which means that there's a range of scores that can be considered scoring 1. You see how, if you see how the 1, the block starts to the left of 1, it starts really at 0.5, and it ends really at 1.5. If you look at the x-axis here, it starts at 0.5, the first block, and it ends at 1.5. Those are called the real limits. So whenever you're dealing with continuous data, you're going to have real limits to each interval, right? Because decimals either get rounded up or they get rounded down, right? So anything greater than 0.5 gets rounded up to 1. Anything less than 1.5 gets rounded down to 1. And you have all these values because it's a continuous variable, right? So I have these real limits to sort of help me with the rounding. The real limit is always 1/2 of the smallest unit of measurement. The smallest unit of measurement here is 1 because if there's a difference between 1 and 2. There's nothing smaller than 1 and 2 listed here. You see 1, 2, 3, 4, 5. They're all separated by 1 unit. So half of that smallest value, the smallest unit of measurement, is going to be 1/2 of 1, which is a half. And that's why the lower limit for the group that scored 1 is going to be 0.5, and the upper real limit is going to be 1.5. So that's important because we're going to use the real limits to help calculate the median for a continuous variable, the precise median. So let's go back to picture B here again. I'll walk you through it. Remember I said I needed 4 blocks on the left of the median and 4 blocks on the right of the median? The best way to do this is divide that column, which has 4 blocks. I only need one of those blocks out of those 4, so divide that column into fourths. And if I take 1/4 of that block, right? So 1/4 plus 1/4 plus 1/4 plus 1/4 will give me 1 block, right? So 4 of the 1/4 of those blocks will add up to 1, and that gives me 4 on the left and 4 on the right because the 3/4 is on the right. And so 3/4 plus 3/4 plus 3/4 plus 3/4 is 12/4. 12/4 is 3, and then add the other block there at 6. 3 blocks plus 6 gives me 4. So that 1/4 of the block divides the distribution completely in half so that I have 4 blocks on the left and 4 blocks on the right. So what I have to do is add that 1/4 to the upper real limit. So if you look at 3, the upper real limit of the category 3 is 3.5. Because remember I said it's minus a half and plus a half as the real limits. So the upper real limit of 3 is 3.5. That's where you see that the line go down over the 3 here. I have to also add 1/4 to that, right, to give me the median, because I need 1/4 of these 4 blocks to give me 4 blocks total. So if I add 1/4 to the 3.5, I get 3.75, and that becomes my precise median for this continuous variable. So all you're doing is taking the upper real limit to the left and then adding whatever you need out of that category in order to divide it completely in half. So I only need one block out of the 4 blocks here listed where the 4 is, right? There's 4 blocks listed that scored 4. I only need one of those blocks. So I only need 1/4 of that column. And that's why I'm adding 1/4 to the upper real limit of 3, which is 3.5. And if I add 1/4 to 3.5, I get 3.75. That's all I'm doing. Find out how much of this column do you need to get the equal number of blocks, and then add that to the upper real limit of the previous number, which in this case was 3.5, and that gives you 3.75. So hopefully that explains it, and there's more problems to come in the homework and stuff that you can practice more on this. But it's not a difficult concept with it broken down simply like this. So the mean is the balance point, the fulcrum, where the fulcrum goes. It's defined by the distance. Remember that the sum of the distances to the means always has to equal 0. These are called deviation scores. We're going to learn about them soon, next chapter. The mean is generally not the midpoint. There's only one, well, there's a couple situations, but the main situation where the median, the midpoint, and the mean are the same is if you have a symmetric distribution. That means the left side is a mirror image of the right side, or vice versa. That's when the mean and the median are the same. The median is the midpoint of the distribution, it's the 50th percentile. The mean is affected by outliers. The median is not, because the median is just a rank order of the scores and then taking the middle part of the distribution. So if you have outliers, the median is not affected. And that the median is the preferred method of finding the central tendency when you have outliers, when you have a skewed distribution, because a skewed distribution resorts from having outliers or having extreme scores. That's why when you have a skewed distribution, the median is a better measure of center. But once again, the problem with the median is that inferential statistics do not allow you to use it. And so if you're using the median, you're going to have to do something called a non-parametric test. And that's not what you want to do. As a statistician, data analyst, researcher, non-parametric test is what you want to run away from, because those tests generally don't get you what you want. They're very weak tests, and they have very low power, statistical power, which we're going to talk about later in the course. That means they're not an ideal choice. They're kind of like the only thing you can do when you have skewed data. Well, there's other things you can do, but there's, people will disagree with certain techniques, and it's beyond the scope of the course. But if you have a skewed distribution and you have to use the median as a measure of center, you have to then use a non-parametric test, which we're not going to even talk about in class, really, because these things are not things you want to do. So as from a researcher perspective and analyst perspective, you want to use the mean. You really love the mean. You love normal distribution, you love the mean, and if you don't have a normal distribution and you can't use the mean, you are basically screwed for the most part. That doesn't mean that your data is a complete failure, but if you tried to publish the median and you didn't use the mean at all and you were trying to publish this, you would be in trouble. Because someone like me would review the paper and say, this is garbage. And like, why is your data skewed? What's going on here? You need to figure out what the problem with your data set is first. And what's going on with the people? Are you measuring the right thing? You need to reformulate your whole research because your distribution is completely skewed. This is not what I want to use. And so if I was reviewing the paper, I would be not happy. Right now, could you publish it? Yeah, you could. Qualitative researchers publish without using any of this stuff. They use the mode. They might use the median. But they just publish with descriptions, right? Descriptive research. case studies and things like that. Uh, could you do that kind of work if your data is skewed? I guess you could try to publish something in that way. Um, but you kind of really have to know what you're doing. You have to kind of have experience doing that kind of research to really know what to get at. And most people doing research that are not trained in qualitative methods or descriptive methods, and they're using surveys, they're not going to know how to fix the problem. They're going to say, we gave out surveys and the distribution was severely skewed, so we used the median, and right away they'd be in trouble. They would be like, well, you're using surveys and you're not reporting the means. What's wrong with the data set? That would be an issue right away. So the bottom line is the median can be a better descriptive measure of center, but that does not make it a useful measure statistically. And that's a little bit beyond what the book is going to talk about. But I'm giving you kind of like real life, like, I look at data all the time. That's basically that's all I do. People ask me to analyze data. I look at all the data. I do all kinds of things. These are one of my interests. And there hasn't been one time where I said, I'm going to use the median in my paper, or I'm going to analyze it with the median, because if you got to that point, you're in trouble. You're not going to find what you're looking for, and you're back on the drawing board. Go back and figure out what happened. Was your sample not representative of the population? In psychology, the population is generally assumed to be normally distributed almost with regard to everything. So what happened? And even if your sample is large enough, you can assume a normal distribution. So it's not like you need your sample to actually be normally distributed. If your sample is above 30, you can assume that the population is normally distributed. And there's a rule for that. It's called the central limit theorem, but we'll talk about later in the course. Not important now, but that's why if you have a really skewed distribution and you want to report the median, yeah, good luck with that. It's not going to turn out well. But for a descriptive purpose, if you're not trying to draw conclusions about the population, it's fine. The median and the mode are great if you're just trying to describe the data set. But once you're trying to draw conclusions about the population, the mean is where you want to go. And even if the distribution is if it's somewhat normal and somewhat skewed, I would say use the mean, because it's just much more robust and you could do a lot more with the mean, as long as you don't have severe skew or severe multimodality, where you have like all these different peaks. I think the mean is the way to go. So here's another slide showing what happens with the outlier. So here 12 is considered an outlier. This distribution of only 6 scores is going to be positively skewed, the tails to the right, because of that outlier. That outlier is now pulling the mean in its direction. So if you look at the other scores, they're around 2 and 3. So the mean would be closer to 2 here, right? If not for this outlier, the mean would be it would be 2, 4, it would be 6 plus 6 is 12. 12 divided by 5 would be 2.4. So if you got rid of this 12, the mean would be 2.4. Once you add the outlier, the mean goes from 2.4 all the way to 4. It's distorting the mean. It's pulling it towards it. It's saying, come here, try to balance things out. You got to come all the way in my direction. So with a small number of data points, all it takes is one single outlier to really distort your central tendency. So 4 doesn't look like a measure of center here. 4 looks like the mean. If I were to look at the median, right, I have 6 blocks. I want 3 blocks on the left and 3 blocks on the right. So in order to get 3 blocks on the left, all I need to do is take those 3 blocks that have a value of 2, right? And the upper real limit of that category that surrounds 2 is 2.5. So if I'm assuming this is a continuous variable, then the precise median of the continuous variable would be 2.5, because that would balance 3 and 3. 3 on the left, 3 on the right. So three blocks to the left of 2.5, 3 blocks to the right of 2.5. So the median, 2.5. The mean here, though, is 4 because of the skew, pulling that mean to the right. So here the median would be a better description of the data set. Could you use the mean? If you were doing, if you were testing a hypothesis, could you use the mean in your measure? Would you be okay justified in doing that? The answer is it's kind of a gray area, right? I would say this is slightly skewed. I wouldn't consider this extremely, extremely skewed. It's skewed, but is it skewed enough that you could, say that you can't use the mean? Well, my advice for this situation is, if you had a situation like this with only 6 data points, I would say you collect more data points, because once you get above 30, then you can use the mean safely. It doesn't even matter what it looks like. You can safely use the mean when you're above 30. But when you're much below 30, then you're in that troublesome area of, should I really, is it okay to use the mean? Or should I really use the median here and then use a non-parametric test? And that's kind of a dilemma. So my advice would be, why you only have 6 people in your sample? My advice would be, go get more people. Don't stop at 30, get hundreds. Although I have run studies at 30, just because they were very costly and I had a lot of people drop out. So sometimes you do get smaller numbers, but six you would never do research with 6 people in your sample. It would be really, really troublesome. It's just not enough. You need to have more than 6. So I would say get more people and then use the mean. True or false? It's possible for more than 50% of the scores in the distribution to have values above the mean. Well, yeah, because if you have a negatively skewed distribution, the mean's going to be in the tail, and you're going to have more than 50% to the right of the mean. So the answer to that is true. Is it possible for more than 50% of the scores in the distribution to have values above the median? The answer is no, because the median by definition is the 50th percentile. So by definition, you can't have anything more than 50% of the scores above it, because that's what the definition of the median is. It's at the 50th percentile. Of course, with the mean could be in any tail, and the mean can be, you could have very few scores below the mean, and the vast majority of scores above the mean, or vice versa if it's positively skewed. I mean, think about the income in America that I talked about. In the US, income. The mean is going to be really pulled far to the right because of the billionaires, the top 1% of the country making all the money. So you're going to have way less, you're going to have way more than 50% to the left of the mean. You're going to have like a huge percentage of the distribution of income is going to be to the left of the mean, because that mean is being pulled all the way up by the billionaires, the multimillionaires. They're making the country look great. Like people are doing well. And then when you hear people living in poverty, you're like, how could you live in poverty? I just saw statistics showing the mean annual income is $70,000. $70,000 for mean annual income. I don't think so. I mean, that's the mean. I don't think that's typical of the country, obviously. It's not typical, but it's being brought up that high because of the billionaires and multimillionaires. It's creating this positive skew. The tail's going to the right because you have these very few people, but they're making tons and tons of money that you can't even imagine. They're basically printing money. If you're a billionaire, what's the point? Like, what's the point of anything? You have like infinite money. So it's like a life that most people will never know, right? The vast majority of people will never know. And if they are billionaires, do they, you know, I mean, you would say like, okay, give like half of your income to charity, but that obviously hasn't happened. I mean, some of them are more charitable than others, but um, what do you do with all this money? Like, at what point does it become, like you just look and you're saying, okay, I have everything I could possibly buy. Now what? That's kind of where these billionaires are at. And in the second scenario, obviously the median is defined as the 50th percentile. So you can only have 50% above the median and 50% below the median. It's the actual 50th percentile. Now we get to everyone's favorite, the mode. And the mode is not very useful uh, in psychology, but it can give you some information. It gives you the score category that is the most frequent. It is generally used with nominal level data, categorical data, because with categorical data, you can't find the mean. So if you ask people like rank your favorite soda, and you give them Pepsi, Coke, Mountain Dew, ginger ale, Sprite, whatever, Fanta, orange, root beer, whatever, and you're saying, what's your favorite one? And then you just compute it, right? That's a categorical variable. That's nominal. You're just asking them, pick the category that you like the best. And then I just count up number of people that like Coke the most versus number of people that like Sprite. That is categorical. That's perfect for the mode. You can't use the mean on that. You can't say, okay, what is the mean of soft drink? What does that even mean? What is the mean of soft drink? It's like you scored a 5 on a soft drink. What does that mean? That means nothing. That means absolutely nothing. Like the number in terms of soft drink means nothing. There's no value there that you can compute the mean, and there's no value there that you can compute the median. It's just number of people that like each category. There's no way to like add up the x values. There's no x values. What's the x value for Coke? Coke. So add Coke, Sprite, Pepsi. How do you do that? How do you add Coke and Sprite together and then get a number? You don't. You don't get a number of Coke and Sprite. You could give it a number. You can say Coke is 1 and Sprite is 2. But those numbers are arbitrary. They're what are called dummy variables. They're meaningless. You can assign any number to it, but you can't add them in any way. It makes no sense. So if you have a nominal variable or a categorical variable, you're going to use the mode because you can't use the median and you can't use the mean because you can't compute anything. You can't sum anything. You can't really rank order things either, so you can't calculate the median that way. The good thing about the mode is it can correspond to an actual score in the data. So a lot of times you compute the mean and the median and no one actually scores the value of the mean and the median. But with the mode, you're guaranteed to have someone scoring the mode because it's the most frequent score. So you have people actually have that precise value. So when I say, Coke, the mode for Coke is higher than Sprite, right? So if I ask for a software drink and 10 people like Coke and 5 people like Sprite, then the 10 is the mode. It's the most frequent score. So Sprite technically would be the mode because that's the value, the X value would be the label Sprite. So people indicate they like Sprite or they like Coke or whatever, and that value is actually the mode. Or if I wanted to look at the mode of scores on a quiz, quiz 1 through 10, I could say 6 people scored a 7 on the quiz 1 through 10. So the mode is 6. Now, could I calculate the average of that quiz? Of course. In that case, I can because the numbers actually mean something. You scored a 7, I scored an 8, this other person scored a 3. That means something. You can add those up and get a logical value. that you can't do with, categorical variables. Uh, so you can calculate the mode with a variety of different types of variables, but the mode is mostly used with nominal or categorical variables, categories, right? You can also have more than one mode. So if you have two modes, you have what's called bimodal. If you have more than two modes, you have what is called multimodal. And if you have no number repeating itself, so that means you have different, everybody has a different value, and no value repeats itself, then you have no mode. So you have no mode, not zero, but no mode. So every number is different, it's no mode. If you have a tie with two categories, it's bimodal. If you have a tie with more than two categories, it's multimodal. Here's what a bimodal distribution looks like. You have one peak around 17, and you have the second peak around 22. Now, 22 is a little bit higher than 17, so there's more people in 22. So if I just want to look at an absolute mode, I would say the mode here is 22. However, when you're describing a distribution like this, if it's close, like if they're close together and they're the two peaks here of this distribution, we generally say this is bimodal. I'm not going to say this is unimodal because 22 has one more person than 17, because that would distort the whole data. If I said this is unimodal and there's only one mode, I would think that I have a normal curve, right? The bell curve. I don't have that, obviously, here, so I don't want to really say that. I have two peaks here, so I want to say the two peaks means it's bimodal. Even if arithmetically, technically speaking, 22 would be considered the mode from a mathematical point of view. In statistics, that would be very misleading because you're trying to describe what's going on here. And if I said the mode is 22, I'm thinking bell-shaped curve around 22. That's not the case here. So I would consider this bimodal, even though they're not exactly equal. For symmetrical distributions, the left half of the distribution equals the right half is the mirror image. The mean and the median are the same, and there's only one mode. So actually, that's technically not true. I could have a symmetrical bimodal distribution. But you can have one mode. So if the distribution is symmetrical, the mean and the median are the same. And if the mode is the same as the mean and the median, so all three are the same, I have a normal distribution. So when the mean and the median and the mode are the same, I have a normal distribution. When the median and the mean are the same, I have a symmetrical distribution. The normal distribution is also symmetrical, right? But I can have symmetrical distributions that are not normal. So I could have a bimodal distribution that is perfectly symmetrical. The left and the right half are the same, but there's two modes there. So that's not a normal distribution. So once again, mean and median are the same, it's symmetrical. If the mean, median, and mode are all the same, it's a normal distribution. And obviously a distribution can have one mode, it can have no mode, it can have two modes, it can have multi-modes. Yeah, it can have a whole bunch of different distributions. I'm going to show you some of that here, besides bimodal and normal. So if you look at picture A, these are all symmetrical distributions, so the left and the right halves are the same. Figure A, you have a normal distribution. The mean, the median, and mode are all the same. In picture B, you have a symmetrical distribution that is bimodal. Here, the mean and the median are the same, but you have two different modes. And in picture C, you have a symmetrical distribution. The mean and the median are the same, but you have no modes. And this is called either a rectangular distribution, because it looks like a rectangle, or it's also called a uniform distribution, because every different value has the same frequency. So the number of people scoring low is the same as the number of people scoring in the middle, is the same as the number of people scoring high. So everybody's equally spread out across all different values on the x-axis. And that's why you get this rectangular situation. Since there's an equal number of people at each level, at each different value, there is no mode, right? You might have one person that scored 1, one person that scored 2, one person that scored 3, one person that scored 4, one person that scored 5, etc. There's no mode there. There's no most frequent category, most frequent number. They're all the same, so there's no mode. And those are 3 common distributions you see. Normal is by far the most frequent you're going to encounter, but you will encounter bimodal. You will encounter sometimes multimodal, where there's 3 or more peaks. And very rarely you'll see something that's uniform or rectangular, but it does happen. So if you look at a skew distribution, the mean is always pulled in the direction of the skew. The median is always more towards the middle, not as extreme as the mean. In the skew distribution, it's more towards the mode. It's closer to the mode. It's going in that direction towards the mode. The mode is generally found in the shorter tail, where the peak is. So wherever you see the peak of the curve, that's the mode. And if the mean is greater than the median, the distribution is positively skewed. If the mean is less than the median, the distribution is negatively skewed. So here you have a mean of 31 and a median of 43. Here the mean is less than the median, so what do we conclude? We conclude negative skew. So the mean is more towards the tail, the left-hand tail of the distribution. The mean is less than the median, so therefore it's a negatively skewed distribution. If the mean was greater than the median, the tail would be to the right and it would be positively skewed. And that's kind of what you see in this slide here. In a positively skewed distribution, the mean is greater than the median, which is also greater than the mode. The mode is at the peak of the curve. And for the negatively skewed, it's the opposite. The mean is less than the median, and the median is less than the mode. So it's the reverse order. Mode occurring at the peak of the curve. Mean is always pulled towards the tail, and the median is pulled somewhat towards the tail, but not as extremely pulled as the mean. So that's an important differentiation to make. So this is just a summary of the mean. So if you know the value of every score, you can calculate the mean because you can calculate the sum of x if you have interval or ratio data. If you do not have interval or ratio data, you can't use the mean. So if you have nominal or ordinal data, don't use the mean. Right? Nominal data, use the mode. Ordinal data, you can use the median. That's okay. Skewed data, use the median. Undetermined values, like if you're missing a large amount of data or you can't interpret the data, there's no recorded data point, use the median. You can always interpolate the values, missing values, but that's tricky and it depends on the situation in which you're missing the values. What's the reason why there's missing data? For the median, if you have skewed distributions, use the median. If it's very skewed. If it's only slightly skewed, you could probably use the mean. But if it's very skewed, use the median. With nominal data, don't use the mean or the median, obviously. With the mode, this is perfect for nominal data. This is perfect for discrete variables, which is basically nominal level data, categorical variables. And if you have interval or ratio data, it's probably not a good measure. If you can calculate the mean, use the mean. That's the best measure of center. It's going to get you the furthest. It's going to not cause you problems. The mode, if I see the mode reported, it better be the categorical variable. If I see the mode reported for, you know, a ratio or interval scale, I'm going to be like, why are you reporting the mode? Like this is like not giving me enough information. So yeah, the most frequent score on the exam was 80. So what? What does that tell me? If I gave you the exam, the stats exam, and the most frequent, the mode is 80, that tells me nothing. So more people scored 80 than any other value. Okay, does that mean people did well on the exam? Does that mean people did poorly on the exam? How do I know? It doesn't give me enough information. But if you tell me the mean on the exam was, 60, that gives me more information than telling me the median was 80. I mean, the mode was 80, I'm sorry. Now, the mean could be influenced by outliers. So I want to look at the mean, and I also want to look at the median. And then I can determine what's going on in the class. But if I just look at the mode, it's not going to tell me much of anything. So I find the mode, outside of nominal data, I find the mode completely pointless. There's no point really to look at the mode. The mean and the median, great. The mode, save for categorical or nominal data. I like to bash the mode. I'm not a big fan of the mode. This graph just shows you what happens if you're missing a lot of data. So here's an outlier. This is similar to the example I gave at 5,000 before. It's not as extreme. Here they give an outlier of 100. So they're showing this as a skewed distribution, but the little wrinkle in the x-axis there, the little bump, looks like an EKG going on there. That's just to show that there's a lot of missing values there because they couldn't fit 16 through 99 on the x-axis. It would kind of go off the page. So they just showed you that it's way out here in the future. You have 100, someone scored 100, one person. So that 100 is really way to the right. It's like off of your screen. It's like way to the right off your screen. But you see that little crinkle basically tells you there's a big gap here, much bigger than it looks like. And that 100 here, that outlier, would have a huge effect on the mean because it's so far away from all the other scores that the mean would be pulled tremendously towards that direction. So if I just calculate it in my head, you have 4 11s, that's 44. You have 110, that's 54. 3 12s is 36, and 54 is 90. And a 13 is 103, and then 100. So 103 divided by 4, 7, 8, 9 would give you 11 and 4 ninths. So 11.44, right? So the mean would be 11.44 if you just looked at the 9 scores on the left of this graph. But now if you add the 100 into the whole picture, right? So now if you add the 100 to the total I found before, 44, 30, 10, 44, 54, 36, 90, 103 plus 100 is 203. Divide now by 10. The mean is now 20. So the mean went from 11.44 all the way to 20. It almost doubled by adding that one outlier at 100. And that just shows you how one outlier in a small data set, especially if that outlier is far away from all the other scores, the further away it is, the more it's going to influence. It really distorts the mean. Because the median here is going to be down here by 11 or 12, right? There's 10 scores here. So it'll be 5 boxes and 5 boxes. So the median here would be 11.5. But then the mean would be over 20. So it really distorts. The mean would be a terrible measure of center in this situation. If I had a continuous variable on my x-axis instead of a categorical variable, I could then plot a line graph, although I don't really like this. The text talks about a line graph here. I generally only like to see a line graph if my x variable is time. So if my x-axis is time, like time 1, time 2, time 3, then I like to see a line graph. I don't really like to see it here with dosage Because if drug dosage is really continuous here, and then I'm measuring two continuous variables, I'd rather plot a correlation. So I'd rather do a correlation and calculate a scatter plot here rather than draw this as a line graph. So the way the text talks about this is not, line graphs should only be used to depict changes over time. They should not be used just to show a continuous variable on the x-axis. It's best to use them just for time and to run a scatter plot unless you have many, many values. If drug dosage here had many values, like thousands of values, that would make more sense. You wouldn't want to apply a scatter plot for that. But with only these 4 or 5 values, you can definitely plot it as a scatter plot, which we'll learn about later in the course. You probably know about correlation and scatter plot, though. So this is a little bit of a non-optimal way of showing this information. This looks a lot better. It's a bar graph. This is showing either means or medians. So a bar graph you would use if you're looking at the means or the medians of categorical or nominal data. So here on the x-axis, I have a discrete categorical data, northeast, south, midwest, west. And on the y-axis, I have a continuous variable. And I'm calculating the median, but you could do this for the mean as well, for these 4 groups. And a bar graph would be a better way. I would even use a bar graph on the previous graph with the drug dosage. I would like that as a bar graph too. They'd be a much more appropriate way to look at it. I don't like the line graph, but bar graph, you see how the bar graph is not connected? Because if I have a discrete variable or a categorical variable on the x-axis, I do not connect the bars. The bars only are generally connected for a histogram. So I would have a continuous variable on the x-axis and a frequency on the y-axis that we talked about last chapter. So if you're just doing a bar graph, if you're looking at means or medians, you have a bar graph, don't connect the bars. Make sure there's space between them. Because the space between them means that they're discrete. It's not a continuous variable here. True, false. The mean uses all the scores in the data, so it's a best measure of central tendency for skewed data. Well, obviously I spent the entire hour and a half talking about how the mean is terrible with skewed data. It's not a best measure of center, so that's obviously false. And if the mean and the median have the same value, the distribution is symmetrical. And as we showed before, that's the definition of symmetrical, when the mean and the median are the same. If the mean, median, and mode are the same, then you have a normal distribution. So the first one obviously is not the best measure, so the mean that's false, and the second one is true. That's the definition of symmetrical. So that's the end for chapter 3. Some real foundational stuff that you probably already know a lot of. If you have any questions, let me know. If not, read the text, follow the lecture, send me emails, come to office hours, etc. And there'll be much more interesting things to come. We have to just get through this foundational material. So bye for now. See you with variance and measures of dispersion next week.